Thank you, everyone. Now, I would like to invite our first keynote speaker, Professor Dr. Habib-ur-Rehman, the Dean of Civil Engineering Department, UET Lahore. He did his PhD in Hydrology and Water Resources Engineering from University of Tokyo, Japan. He has authored more than 70 publications, indexed in several databases including ISI and Scopus indexed journals and Proceeding. His area of expertise are physically based distributed hydrological modeling, regional scale soil erosion, and sediment transport modeling. Please, sir.
Okay, can you see my slides?
Ji, sir.
I have shared slides. Okay, so in the name of Allah, the most beneficent and the most merciful, Honorable Chief Guest of the International Conference, Mr. Muhammad Mohsin Khan Lagari, Minister for Irrigation, Punjab, Honorable Vice Chancellor, UET Lahore, Professor Dr. Syed Mansoor Sarwar, Respectable Director, Center of Excellence, Water Resources Engineering, UET Lahore, Professor Dr. Noor Mohammad Khan, highly learned keynote speakers, presenters, faculty members, and participants of today's International Conference on Water Resources. Assalamu alaikum, Ohayo gozaimasu, Nehao, and good morning. I am highly thankful of the Director, Center of Excellence of Water Resources Engineering, who has given me this opportunity to talk as a keynote speaker in this international conference. Dear participants, today my topic of talk would be monitoring and modeling MAR techniques for groundwater recharge. MAR means Managed Aquifer Recharge Techniques. This would be the sequence of my presentation. I would give you some introduction about the MAR and then the MAR techniques, then the objectives of today's presentation. Then I would discuss the large diameter recharging wells, and then the infiltration galleries, and then the methodology which we have adopted. Our MSc students, they have carried out research on the large diameter recharging wells and the infiltration galleries. So then I would like to discuss the results, and finally I would share the concluding remarks, and at the end I would like to give you recommendations based on the research findings and my experience. Unfortunately, when we are doing urbanization, what we do, we increase the impermeable areas, which reduces the infiltration of the water to the ground. And at the same time, what we do to give water to the large population and to fulfill the needs of the water demand, we extract water through pumping. So all these acts, they decrease, they lower the water table in any area. So at an average in Lahore, the groundwater depletion rate is alarming. It is near 1 meter per year. And this shows that the recharge to the groundwater is lesser than whatever we extract from the ground. So that's why our groundwater reserve is depleting. So modern techniques to recharge the groundwater are rainfall harvesting. That is delay action dams, bank filtration, infiltration ponds, infiltration galleries, and recharging wells. The recharging wells could be small diameter recharging wells or large diameter recharging wells. UET Lahore, in collaboration with LDA, had installed 4 large diameter recharging wells. We will talk about them in our Junaid Jamshed Cricket Stadium. And then we have carried out research, we have monitored it, and we have carried out its modeling through our MSc research students. The another piece of research work which is carried out by the Center of Excellence in Water Resources Engineering, UET Lahore, is basically the provision of infiltration galleries in one of the town, which is model town, and to see its impact, how these infiltration galleries, they are improving the groundwater recharge. So based on that, so I have selected this topic, that what MAR techniques are suitable for us and which are beneficial for us, which are cheaper and which we can easily install. Hanged. I don't know why it is hanged. Hanged. Yeah. Is it shared or shall I share you again?
Sir, it is visible.
It is visible. Good. I don't know why this happened. Never happened before. Anyway, now I would like to discuss several more techniques. One is the ASR, aquifer storage and recovery. You know, it's the same recharging well and the two well are pumping well. So we recharge the rainwater inside and also do the pumping. Another is the ASTR, aquifer storage, transfer and recovery. So the rainwater is being recharged through this recharging well, and nearby there is a pumping station, and from here there is a pumping well and we can pump water. The another is the drive well. So these recharging wells, they are used to raise the water table, and nearby we can install a pump to supply, to fulfill the water demands of the community. Another MAR technique is percolation tanks, the delay action dams. Maybe we can have a small dams, and then this water infiltrates in ground, and in that way it raises the water table. Another MAR technique is rainwater harvesting by collecting the rainwater from the rooftops, and then that we may use to recharge the ground, and we may raise the water table, and that we can utilize for fulfilling the water demand through groundwater. The bank filtration, you know, along the rivers and along the canals, there is a seepage of water if the canals are not lined canals, and then here in the vicinity of the canals or rivers, if we can install pumps, they don't affect much to the groundwater reserve, because the water which is coming through seepage could be used for pumping. And the next are the infiltration galleries. The rainwater is stored in these narrow trenches, which are filled with boulders, and then the water seeps down and can raise the water table, and then we can do the pumping nearby. And the another is the dune filtration, and the next is infiltration ponds, to which we can say that deep parks, and from the surface runoff can go to these deep parks, and then through water can infiltrate and seep and can raise the water table. And I think this one is the cheapest and the most efficient solution of the the MAR technique to recharge our ground. Now I would first like to discuss the large diameter recharging wells, on which the research has been carried out by our MSc student. And these 4 recharging wells, these which are shown in orange color, these were installed basically by UET in collaboration with the LDA. And these are very large diameter recharging wells. The diameter is about 15 feet and the depth of the recharging well is 30 feet. So it has a capacity of about 150 cubic meter of water. So this is the inlet to this recharging well, and these 4 recharging wells were provided. And water enters from here. Then, what happens once there is a rainfall, and if it's a high intensity rainfall, then the surface runoff generates and it flows through these catch pits. And then these catch pits, there is a sewer line, and that pipeline takes water to this sump, and this sump then provide this water to this recharging well. And then the recharging well gets filled. So it means that this is very good to control the surface runoff. So it doesn't allow flood inundation. And whenever even there is a very high rainfall, so water immediately goes in this well. And once the water level rises here, then there are holes which are provided in the walls of this well. And then water moves in the ground and the lateral outward direction. So this is the main working of the large diameter recharging wells. This is the construction process of these large diameter recharging wells, the excavation and the wall pad formations, and this is the sinking of the well masonry. You can see that masonry wall, and here this is the masonry work completed, and this is the filter material which was filled in between. And as the water could, seep in lateral directions. And this is the top cover with a hole to monitor inside and for the recharging well. This is the construction process of the mini catchment pit and the runoff collection. So this is the one sewer line. This is another. So it acts as also manhole, and the sum of the the silt can deposit inside, and this is its covering. This is how the construction process was going on, and this is the final shape of the catch pits. After once these large diameter recharging wells were installed in this Junaid Jamshed Stadium, then what we have observed on 3rd July 2018, 252 millimeter rain occurred in one day, and this is the photograph at 3 p.m. So you can see that this is an XC ground of the UET Lahore, which is very close to the Junaid Jamshed Stadium. And here you can see that there is flood inundation. The water is stagnant over here, and here, due to presence of that large diameter recharging wells, the water has disappeared from the surface. So this is the beauty of large diameter recharging wells. The objectives of the MSc research work were to install flow meter and piezometer to monitor groundwater table fluctuations. Unless we don't do instrumentation on these devices, we cannot measure their performances. So, and the second was the assessment of groundwater depletion rate without recharging wells, and then to assess the groundwater depletion rate considering the recharging wells. So what was the benefit of these recharging wells? So in terms of efficiency, in terms of avoiding ponding to the surface. I think the light has gone, power is off, but I think you can see me, huh? Now the methodology adopted was certain data was collected, like the rainfall data, groundwater data, which includes water levels, pumping wells, recharging wells. And in the data analysis, temporal distributions of the rainfall and groundwater levels were computed and plotted, and the depletion rates were computed for the groundwater table. Then the next step was installation of our equipment, like the flow meter for the volume measurement, that how much water is entering in the large diameter recharging well, and the two piezometers were installed to know the position of the hydraulic grade line underground, and then assessment of groundwater table positioning using a MartFlow software. So without recharging well and with recharging well. Of course, without recharging well, proper calibration was done of the model and the validation was done. And similarly for with recharging wells, as we were having data as we collected from our flow meter and the piezometers, so we did calibration and validation. And this data was collected like topographical data from Google Earth, bore log data, for thickness and hydraulic conductivity, which we collected from WAPDA and SPAC, and daily precipitation data from PMD Lahore, and the piezometric data from WASA and UET Lahore, and the pumping well data from WASA and UET Lahore. So this was our model domain. We took a very large area, maybe 5 to 6 times more than the over area of the Junaid Jamshed Stadium. And as I mentioned you earlier, these were over 4 recharging wells, which were provided in 2018 June. And how it is working, that these CEWRE lines, pipelines, they are provided in such a way, they have the slopes in this direction. So it means the quarter of this Junaid Jamshed Stadium is contributing to any one of the recharging well, which is shown here. So when there is a very little amount of the rainfall or less intensity of the rainfall, in those days, water doesn't go in this large diameter recharging well. This is the beauty of this large diameter recharging well. Only the water infiltrates directly through the grass and into the land. But when the rainfall is of very high intensity, then what happens? The water enters in this CEWRE through these catch pits, and then from both sides, and then it enters in the large diameter recharging well. So it becomes effective, and it becomes active when there is high intensity rains and when the surface generates over the surface. This is one the data analysis which we collected from 2015 to 2018. So these are the rainfall distributions of each year, and the water table level was around 175 meter in 2015, and then it has further lowered down, and due to this heavy rainfalls it has slightly improved. And then in 2018 there were very little rainfalls in Lahore, and due to that the water table has gone further down. So these are basically the plots of our observations of the observation wells. So there were 2 observation wells, and this observation well OW2 is close to the recharging well, and this is away from the recharging well. And you can see that these shows some rise in the water table when there are rainfall events. And this is the analysis of the data and the contour maps of the water table in 2015 and 18. And from here, what we have computed that average depletion rate of the groundwater table is 0.81 meter per year. This is again water table elevation without recharging wells for this period from May to November, which is basically was the summer period. And here the depletion rate was minus 0.08. So in summer, groundwater depletion rate is always much lower, even negative. Instead of going down, it is coming up. But in winter, it goes down because we have very less rainfalls. So this is again the water table elevations in winter. And here the depletion rate was reported and computed as 0.84 meter per season. And these are the water table elevations when we provided the recharging wells. And depletion rate was for the season, winter season, was reduced to 0.45 meter from 0.84 meter. Now this is the installation of the flow meter. So this was a flow meter which we have installed in the sump, and from here we can observe. So this is how the observer can see the dial of the flow meter, and this is the whole is the installation process. And then this is the installation of the piezometers, the standard pipe, and how they are fixing. Installing in the ground. And then this is on this slide, it is shown that how the levels were shifted from the benchmark to the observation well. And these observation wells are kept in lock. When we have to take reading, we have to open it and we insert the the stick inside. And these are the the stress meters which we have used for the modeling. This was the model setup with this data. And the pumping wells, we used 12 pumping wells. 5 pumping wells were of UET, 5 of the WASA, and the other was also from WASA within the model domain. And the pumping discharge we computed from the capacity of the pump and the duration for which the pump was being operated in a day, in winter and in summer. Then the calibrating parameters used, particularly hydraulic conductivity and the storage, the coefficients, and the initial head we took as 174.8 meter. And then the boundary conditions, basically wearing head boundary condition was provided. And after that, the model was calibrated for a period from 2015 to 2016. And you can see that for different periods, these are the results of model calibration, which shows very good match with the observations. Then the model was validated from 2016 to 18, and we can see that model has good validation results. Then these are the contour maps which were prepared for the 1st and the 7th stress period. And now this is the again modeling started for using considering the recharging wells. And
Habib sir, may I request you to conclude in a couple of minutes?
All right. So then these are the volume calculations. If you see that here, only 20 millimeter rainfall occurred, and 4.73 cubic meter was the volume of surface runoff which went into the recharging well. But the capacity was 150, and when there was a rainfall of 35 millimeters, only 42 cubic meter of the water entered as surface runoff. The capacity was much higher than it. And these are the calibration results, which are within the 95% confidence limits. These are validation results, and these are the results that due to the water when there is in the recharging well, how this hydraulic grade line changes, and when there is a lot of water comes here, its slope becomes like that. These are the depletion rates for summer season, -0.72, winter season 0.48, and per year average 1.02 meter. And then the next was the study carried out by one more MSc student, was the infiltration galleries. And the area was selected was of Model Town, having 592 hectare, and and these are the proposed, the infiltration galleries, which are you can see in this color and purple color, and total galleries were 180, having a hectare of having an area of 4.3 hectare. These galleries were provided over the green belts, parks, depressions, and side of parks. And now these are the concluding remarks based on these two studies. Large diameter recharging wells in this study area have reduced the average groundwater depletion rate by 0.39 meter per year, considering winter data. Whereas infiltration galleries in the study area have reduced average groundwater depletion rate by 0.15 meter per year. It means that the large diameter recharging wells are more efficient. So large diameter recharging wells are more effective in reducing the groundwater depletion rate and flooding on the surfaces due to large capacity of recharging wells. Small diameter recharging wells locally rise the water table and are not much effective in reducing the flooding on the surface. Clogging of filter material, is a very serious problem in all types of the recharging wells and infiltration galleries. So we need to clean it every year before monsoon season, otherwise they become totally ineffective. Infiltration ponds, to which we call as deep parks, in Punjabi we call as dungi grounds, are, I think, the cheapest and the most effective means of groundwater recharge with practically no issues. Now my recommendations. Large diameter recharging wells are recommended with certain modification to recharge groundwater and very good for managing the flooding. And infiltration ponds, means the deep grounds, are recommended for quick urban flood management and groundwater recharge being most economical solution. And I also recommend that before launching any urban society or housing society, groundwater hydrological studies must be carried out, and the approvals should be given by the LDA, by other authorities, after having a proper, appropriate groundwater hydrology study. And with this, I would like to conclude my presentation. Thank you very much.
Thank you so much, sir, for sharing your valuable knowledge.